Hi everyone, make sure you have a copy of these notes in front of you as you start watching this video. We are going to be talking about the electrons and where they all are according to Schrodinger's model. Remember, Bohr said they were on rings, which he called orbits. Schrodinger says that the electrons are in orbitals, which are areas where there's a high probability of finding the electron. It's a little confusing, but we're going to be able to use the periodic table as a cheat sheet to figure out where all of those electrons are for any given atom. Let's start here on the first page. An electron configuration is a way to show the arrangement of the electrons in an atom, meaning what orbitals they're in. In order to do this, we need to know 3 rules about how to write electron configurations. The first rule is that orbitals can only hold 2 electrons, and that those electrons must have opposite spin. If we simplify it a whole lot and picture an orbital as just this line here, the electrons must be one spinning up and the other one spinning in the opposite direction. We'll often draw them this way. It's a little bit weird why that works, but it's that electrons are negative and so they don't want to be near each other. But because they're negative, if they start spinning, they make a magnetic field. And because they're spinning in opposite directions, those magnetic fields are opposite, which opposites attract, so they'll share space in that orbital. Bottom line is every orbital can only have 2 electrons and they have to have opposite spin. The second rule is called Hund's rule, and it says if 2 or more orbitals have the same amount of energy and are available, only 1 electron will go in each before they start to pair up. This is also known as the bus rule. And the reason is because it kind of works like seats on a bus. If there are 3 seats on a bus and they're all available, when you walk onto the bus, you'll sit in the first one. And when someone else gets on the bus, they don't sit down right next to you. They're going to sit in another empty seat. And then someone will sit in the 3rd empty seat. And now the 4th person who gets on the bus, then they're going to have to sit with someone. But if there are other available empty seats, they'll take the empty seats first. Degenerate orbitals are orbitals with the same amount of energy. Just like these 3 up here, they have the same amount of energy. So we have a special term for that, and they're called degenerate orbitals. The last rule in writing electron configurations is Aufbau's principle, and it says that lower energy orbitals have to fill before higher energy orbitals. So the first one, 1, has to fill before 2, before 3, just like you would count. And sublevels have to fill S before P before D. That sounds a little confusing now, but we'll talk more about it later. Why is the 1s orbital lowest in energy? It's because it's closest to the nucleus. The 2s is higher in energy and it's further from the nucleus. But it's kind of hard to remember the order that the orbitals fill in without having sort of a cheat sheet. That's what we're using the periodic table for. On to the next page of your notes. You might want some colors to do this in. Colored pencils or highlighters will work fine. Start by moving helium over. Then outline the 4 boxes that the periodic table creates. Label the first box S, the one on the right P, the one in the middle D, and the one at the bottom F. Now you're going to number the rows. Those are the same as the periods that you learned about in the periodic table presentation. Label those rows in the S block and also in the P block. Notice the P block doesn't have anything in the first one, so that will start at 2. And then you go down 3, 4, 5, 6, 7. The D block is a little bit weird. That's row -1. So even though this is the 4th row, it actually gets a 3, and so on. So 3, 4, 5, 6. The F block is really weird. They're row -2, and we're not going to worry about them so much, but just if you're curious. Those rows would be numbered 4 and 5. You're probably wondering why those numbers are a little funky, but it's because orbitals that get further from the nucleus start to get closer together. And when they get closer together, there are some energy overlaps between the energy levels. So the energy levels are 1, 2, 3, 4, 5, 6, 7. And just like in Bohr's model, where the rings started to get closer together, in Schrodinger's model, the energy levels start to get closer together, and then they do start to overlap. Now that your periodic table is all set as a cheat sheet, we're ready to learn how to write electron configurations. There are 3 ways to write electron configurations. One is called orbital notation, another one is called the full electron configuration, and the last way to write them is called the noble gas core. We're going to write each of them, and we're going to do it first for the element chlorine. Chlorine has 17 electrons, and we know that because it has 17 protons, so if it's neutral, it has 17 electrons. In order to write the electron configuration, we're going to start right at the beginning with hydrogen, and we are going to read just like you would read a piece of paper. So this first hydrogen is in the first row, and it's in the S block, so it's 1s, and there are 1, 2. And then we're going to keep going across. Now we're at 2, 2s, 2. We're going to keep going across. Now this is 2p, because it's the second row and it's the p block. 2p, 1, 2, 3, 4, 5, 6. Okay, so we're going to follow that pattern, and we're just going to read straight across the periodic table until we did get to chlorine. So we're going to write just a horizontal line to show the orbital, because they're kind of annoying to draw, right? It would be a sphere, so we're not going to draw that. And then we're going to label it as the 1s, and then we're going to put 2 electrons in it. And we draw the electrons as little half arrows. You can draw them as full arrows if you want, but I generally draw the half arrows just because they're a little less annoying to write. And then we're going to put a slash. That's going to show that we're moving from the 1s, where we did 1, 2, on to, there's nothing else in this row. So now we're on to the 2s. So here's the 2 in the S block, and we're going 1, 2. So we're going to go 2s, and we're going to put 2 electrons in there. And then we're going to keep going all the way across. I'm going to put a slash here to show that we're at a new spot. And now we're at 2p. Because we have to draw 3 lines, because we're only allowed to put 2 electrons in an orbital. Also remember, we drew the p orbitals, and there are 3 different ways to draw them. You can have the px, the py, or the pz. So we're going to label this 2p, and we're going to put those electrons in, and I'm going to draw them in following the bus rule, right? So 1, 2, 3, 4, 5, 6. We're not at chlorine yet, so we need to keep going. I'm going to start a new set of orbitals, because we've gone all the way through the 2p's, and now we're at 3s. Remember, s's only get 1 orbital. And then we're going to draw a slash, and we'll move this guy out of the way for us. And after 3s, we've got to keep going across. Now I've got 3p, 1, 2, 3, 4, 5 will get us to chlorine. So we're going to draw 3 lines for p's, 3p, 1, 2, 3, 4, 5 electrons. Let's double check that that included 17 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. That's because we counted each box as 1 electron. Notice S's always are going to get 1 line. P's are always going to get 3 lines to represent their 3 orbitals. And if you remember, the D's have 5 different orientations. And if you didn't remember that, you can also look and see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes, which means that you're going to need 5 if you can put 2 electrons in each box. We're not going to do the F's, but I bet you could figure out how many we'd need for them. Again, orbital notation is the hardest one to write. It's a lot of drawing. Full electron configurations are a way to express the same thing, where all the electrons are, with a little less information and also a little less effort. So the way you would write this is you would start with 1s and just write an exponent 2 to show there are 2 electrons in that orbital. And then 2s with an exponent 2, and then 2p with an exponent 6, 3s with an exponent 2, 3p with an exponent 5. That shows you where all the electrons are in chlorine. It doesn't show that things are spin up or spin down, and it doesn't show that the p's have 3 separate orbitals, but it still gives you a lot of the information that you need. The noble gas core is kind of a shortcut for writing electron configurations. You get to start at the noble gas before the atom you're trying to write an electron configuration for. So if here's chlorine, we get to start not at the noble gas after it, but at the noble gas before it. So we get to start at neon, and then after neon, we just have to write the full electron configuration. So we're starting at neon, that's number 10, so that accounts for 10 of the electrons. And then we do 3s2 and then 3p5. So basically the neon accounted for all these electrons, which is actually the electron configuration for neon. Let's try the electron configuration for arsenic. It's over here on the periodic table. You can tell this one's going to be a little longer because it has 33 electrons instead of just chlorine 17, but all electron configurations start the same way. So we start with a 1s2, right? So we start right at the beginning, 1s2, then keep going across, there's nothing there. Now we've got 2s2, and then keep going across. Now we're at 2p, and the 2p gets 1, 2, 3, 4, 5, 6. Then we're at 3s, and we'll go 3s2, and then 3p6. And now it's new because we passed chlorine, so we're at 4s2. And then here's where it's a little bit weird, right? So we're gonna do 3d. Remember, for the D's, we have to do 5 lines. 1, 2, 3, 4, 5. And we'll fill them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 3D. So we did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're at 4p. And to get to arsenic, we only need 3 electrons. So 1, 2, 3, because p's always get 3 lines. 4p, and then we're going to draw our 3 electrons. 1, 2, 3. Writing the full electron configuration after you've done the orbital notation is pretty easy. Why don't you try pausing the video now and see if you can write it and then check it. Check your answer. Hopefully you have what I wrote. The last one is the noble gas core. This electron configuration is one that's a lot easier to write a noble gas core for. So arsenic is right here, number 33. The noble gas before it is argon. So we're going to put argon, which argon will account for the first 18 electrons. So that gets you all the way to here. And then after that, we're starting at 4s. And those 2 electrons, then the 3d10 electrons, and then the 4p3 electrons. Sometimes it's easy to get lost in all this notation, but remember, what we're doing is we're trying to say where all the electrons are for any given atom. These 2 atoms, one's chlorine, the other one's arsenic. We're trying to account for where all the electrons are according to Schrodinger's model. While we haven't finished this note sheet yet, you should be able to do some practice in electron configuration practice part 1 if you're in college prep, or in the first page and most of the second page of the electron configuration practice problems. Work on those for a little bit before you watch the second video.